Why is it not?
No, I was talking about on your own device.
Oh, I thought you wanted me to guess.
Guest speaker.
Mm-hmm.
Our first guest speaker here.
Jaden asked if I wanted to hop on, and I thought he meant as a guest. Rude. Rude.
Let's see. There it is. Found it.
Okay. Hold on here.
Oh. Nice. Okay.
All right. Should we get going here?
Sure. Are there any questions? Nothing popped up in the last couple minutes, right?
Nope. Not that
Okay.
I'm aware of.
Well, as you can see, we have turned dark, right? Our whiteboard is now a blackboard. Hopefully you can see our writing a little bit better this week. We had somebody tell us that it was a little bit difficult to see on the whiteboard, so that's why we changed it up.
And we're going to be talking about orbits, so it's very fitting for space.
Oh, yeah, let's throw in some stars.
Dude, here, I'll draw some stars.
Yeah. This one was my favorite. I'm gonna use a laser.
Yeah.
I really like that one. I really like that one.
Woo!
Yeah, so should we just jump into it? Talk about orbits, why the force of gravity is important for orbits, and how without it we wouldn't really have much of a solar system and much of a galaxy and all of the other things.
Yeah. Let's talk about that. And on top of it, I think by the end of the night, we can somewhat debunk the flat Earth theory. We'll have that somewhat debunked by the end of the night. However, that's if satellites are real, but we also know that that's a conspiracy theory from NASA. So there's no such thing as satellites up there. So Jaden, let's start off with a thought experiment to understand orbits, okay? This is something that Sir Isaac Newton talked about, all right? So I'm going to draw a circle here, okay? I'm going to draw this, okay? This is a mountain, okay? And then on top of this mountain...
Okay, that's a very tall mountain for that.
Okay, we'll draw it smaller, okay? Sheesh.
Oh, no, I loved it. I loved it.
Okay. And let's say there's a cannon on top of this. I know this is not to scale, okay?
Why don't we use like Superman so we're not super cliche?
You can have Superman and I'll have my cannon.
Okay.
Okay, so from there we can go ahead and Jaden, what happens if we shoot a cannonball or we just drop a cannonball right here? What do we know about gravity? What will happen if we just drop it from the top of that mountain?
It will just fall straight down to the earth, assuming there's no other forces acting on it.
Okay. So now what happens, Jaden, though, if I shoot a cannonball and it now, it's got a velocity going this way?
Okay, well, we know that the force of gravity will still act on it, and if it has a velocity going that way, so that tangential velocity, we know that we have a projectile motion now, and it will fall, boom.
Okay. And so, like you said, the force of gravity, right? So the force of gravity is from the radius or the center, right? It's like the center from the Earth or whatever mass we're talking about, and it is always going to be pulling directly in. So if we were to take this point here, the force of gravity would be taking this cannonball and pulling it in right there, right towards the center. And so, but at the same time, like you said, this cannonball is moving, right, in a direction.
Right.
And so it's getting pulled in, but it's also moving, and so it's falling, and like you've drawn, it will eventually hit the Earth, right? Because it's falling,
Right.
but it's falling kind of close to the same as the curvature of the Earth, right?
Right.
So then from there, Jaden, what happens if we shoot this cannonball fast enough so that it's falling, and then it just...
Okay, so if we have a great enough tangential velocity, it will just continue falling. I'll just continue from this circle. It will continue falling, and it will come back and hit the cannon in the backside. All right, and that's assuming we have a strong enough tangential velocity.
Right. So what we just described essentially is what an orbit is, right? If something's falling fast, or if it has a large enough tangential velocity, it will continue to fall, right? And it will fall at the same speed essentially as it's getting pulled into the Earth. And so it is constantly Earth changing its velocity, changing its direction of its velocity so that it keeps curving.
Yep.
Now, Jaden, what would happen if we shot this cannonball super duper fast?
Okay, so it would still be affected by gravity, but this time I'll draw a new one. It will go around and then it will shoot off. Like so. This might not be the exact shape. It will look more like a parabola type shape, or even like a hyperbole type shape. Hyperbola, sorry. And that is kind of the idea behind it. It's like a big slingshot.
Exactly. So it's like if you were to have, a ball on a string, right? And you whip it around, woo! Then all of a sudden the string kind of snapped, right? And so then you know that it would go flying off. And that's the same thing. You can think of the force of gravity as that string holding a ball towards the center of the Earth, right?
Yeah.
Cool. By the way, for anyone that is watching, you are more than welcome to ask us a question at any time. So please feel free to ask any questions either by emailing us or
typing in the chat.
Yeah, typing in the chat. We're here for your questions. But in the meantime, continue to solve for this. So.
Okay.
Next slide. So we just talked about, that was a visualization of what an orbit is. Very brief, straight to the point. So now let's talk about the math behind it, okay? So remember, there's this equation, Jaden, right? Which is F equals ma, right? Where is the mass?
And isn't that like one of Newton's laws, or something like that?
Dude, it is one of Newton's laws.
Sweet. Okay, so force equals mass times acceleration.
Right. Where mass is one of the mass is one of the mass of the object, and then acceleration. Remember, acceleration is how quickly its velocity is changing. Okay.
Okay.
So from there, we can go ahead and there's another equation for the force of gravity, which is this. G, sorry, whoop, F of G equals big G, which is the gravitational constant, times
Okay.
mass 1, okay, times
Okay.
mass 2, and this is divided by the radius squared. Okay.
Okay. And with the minus sign out here, right?
Yeah. Don't forget your signs. Signs are important.
Yeah. And the little g with the force, like the F, right? F of g, that just means the force of gravity in this case. Right?
Right. So that's the force. So, sorry, let me back up a little bit. We need to talk really quickly what the force of gravity is, I guess. So the force of gravity, we can see from this equation, is related to two masses, right? Up to this point, we've been dealing with just a single mass. But every object is attracted to another object by gravity.
Like
right?
Romans?
Yeah. Just like that. I actually have a shirt designed that I'll maybe show later on tonight that is about the force of gravity, and the punchline goes something like, the closer we get together, the harder I fall for you. It's pretty clever.
That is pretty clever.
Because see that r squared, as that gets smaller, the force of gravity, right? The closer you get to something, the closer two objects get together, the stronger that force of gravity is. And so, so my shirt says, anyways, that says what I said that I'm forgetting now. But, so we've got let's keep working here.
We have a couple of questions in the chat. Kelsey says, I want to see both of your sweaters and see whose is cooler. That's not much of a question. It's much more of a demand, and we are kind of fresh out of demands. But Carsey says, why would anyone know any of this? Why would someone just know this stuff, Kip?
Well, I don't know if many people just know this stuff. I went to school for it. Jaden, you went to school for it. But on top of that, most of us do experience gravity quite frequently, right? Like if you were to drop a pencil.
You mean every single second you've been alive, you've experienced it?
Exactly. It's like that, in the Flat Earth documentary, they're actually talking about why they don't believe the Earth is flat, and one of the reasons why is because we're rotating so fast, right? And well, then why can't we feel it? And part of that's thanks to gravity sticking us to the same spot, and that's why we can't feel it. So, but as far as the mathematical equations go, that's when you need to go to school to have someone teach you, or you can tune into Aftermath and we'll show you. So hit that subscribe button down below. Anyways.
Hey, yeah. Okay.
Okay.
All right.
Thanks for those questions. If anyone has any other questions, please let them know. By the way, my sweatshirt is better. It has a throwing up unicorn on it. So.
Okay, I'll give you that.
Okay. So let's get back to some aftermath here. Okay.
Yeah.
Okay. So, Jaden, we can do something, right? We can plug in this F.
Right.
Oh gosh, I'm on my eraser. We can plug in this F for that F. So we can get MA is equal to g times m1 times m2, thank you,
You're welcome.
r squared. So then from there, we can go ahead and
And what mass is the first one talking about? It doesn't have a 1 or a 2, so what mass is that representing?
so yeah, so this mass we're gonna say is equal to the mass. We can choose whatever mass we want, right? Because of Newton's laws, there's an equal and opposite reaction to everything, right? So the mass that's acting on
Right.
the force that's acting on mass 1 is the same force that's acting on mass 2. So all that matters is we just need to decide which mass we want to work with. Normally, we'll say mass 1 is, the Earth in this case, and we'll say that mass 2 is our satellite.
Okay.
So we'll say that this is
Okay.
mass 2. Okay?
Okay.
And so from there, we can actually go ahead and we can cancel these two masses out. We do have a questions coming in though, about
Oh, yeah.
contrails. I'm not sure if I know the answer to those ones, but
What? Why does a contrail approaching you from the horizon look like it's going up, and contrail going away from you on the opposite horizon look like it's going down? Then Kelsey comments, "What is a contrail?" I am on the same boat as Kelsey. I don't know what a contrail is. And then Carsey says, "Well, that was from Brad, the contrail question."
yeah. So a contrail,
Contrail is a
Jaden,
French
is
word. Okay.
contrail, Jaden, is that thing that you see behind the plane, right? When you're the
Okay.
chemtrails, actually, Brad has it wrong. It's actually a chemtrail. They're dumping chemicals, and that's why we see what we see. As far as Carsey's question about what's the difference between mass and weight, if Carsey would have been here on one of our earlier videos, we would have had the answer to that already, but that's all right. We got new subscribers, so we'll go ahead and answer that this time. So for Carsey, mass is how much of something exists, right? It's the total amount of stuff. Whereas weight is the force, or yeah, it's gravity acting on that mass. So for example, when you're on Mars, whoa, dude, I just got attacked by something. When we're on when you're on Mars, your weight is different than your weight on Earth because of
That.
that, but your mass stays the same.
Yeah. Hope that answers your question.
Yeah.
Okay.
So I got an email question, which is actually exactly what we're working on, which is how does a satellite work? So that's pretty good.
Okay, awesome.
We'll come back to the contrails question later. I'm not quite sure exactly what they're asking.
I think that just has to do with the curvature of the Earth and how if you're looking into the horizon, it might look like it's coming up at you, and it could also look like it's going down, like in the same situation. I don't know, just different perspectives. I don't
That's
know.
good. I don't have the math for that. Sorry, Brad. We'll have to come back to that one later. So back to our orbits question, right? So we now have this equation, which is the acceleration of the object is equal to the
And
gravitation. What?
So, Kip, when you just crossed out M2 on both sides of the equal sign, what exactly happened there? Just to
Dude, do you
clarify.
want me to tell you what happened, dude? It was
Yeah.
it was math magical. But but the
Wave
how
the hand.
yeah, dude, just wave the hand. It's actually, I mean, it's something that I know from intuition. If you have something that's, being multiplied on both sides, you can cross them out. But the reason for that is if we're trying to get acceleration by itself, we can divide
Right.
this M2 on both
So we're
sides.
using inverse operations
Right.
to divide M2 on both sides. Okay, and it just cancels each other out. Anything divided by itself equals 1, and
Right.
1 times anything doesn't change the problem. Okay, cool.
Cool. Darcy responded, by the way, saying the answer to the contrail question is because the Earth is round. So, Jaden, you are correct.
Sweet.
Okay.
Okay, so we have our equation here. Acceleration equals big G times m1. All of that is divided by r squared.
Right. So,
Okay.
Jaden, do you notice anything interesting about this equation that might stand out to you that, I don't know, is significant?
Well, the big G and the m1, those are constant, right? Because 1 is the gravitational constant and m is the mass of the Earth, which, as far as I know, isn't changing all that much, and that's what I've noticed. What about you?
So, yeah, that's true. And then the other thing that I've noticed on top of that is that our acceleration of our object, thanks for that negative comment again. The acceleration of our object has nothing to do with its own mass, right? So it actually, the acceleration has nothing to do with how, what the mass of the satellite is. It could be this massive, massive satellite, and it doesn't matter, right? The only thing that
You're
matters,
telling me that this massive, massive, really, really heavy satellite would be affected the exact same as a piece of paper?
that's what I'm telling you.
What the heck? Why is that so hard to believe? But the math shows exactly what we were just saying.
Exactly. It only depends on the mass, or around what the other mass is, right? So if
Okay.
it was the other way around, if we were trying to figure out what the acceleration of the
Earth.
acceleration of the Earth compared to the piece of paper, the mass of the Earth wouldn't matter, but the mass of the paper would.
That's
So
crazy.
a little bit of math there for us.
Yeah.
Okay, so let's keep moving forward. The goal of tonight is we want to be able to calculate how fast something's going to have to be going to stay in orbit, depending on the radius at which it's at. Okay.
Okay.
So from there we can go ahead and say that, well, let's think here. What
So
should
we
we do
get a
next?
new page, or
Sure, let's get a new page. And
we can.
I will write that equation here again. So A equals G mass 1 over R squared. Okay. So now from here, so for those that need a quick refresher, acceleration is the changing of velocity, right? So that doesn't necessarily mean that it's slowing down, right? If we're in two dimensions, it would either have to be slowing down or speeding up, right? You'd have this,
Right.
or maybe not two dimensions. I get one dimension. Sorry, if we're in one dimension, it'd be slowing down or speeding up. But
Right.
because velocity is a vector, it has direction associated with it. So the acceleration isn't just the slowing down or speeding up, but actually the change in direction of velocity as well.
Okay, so you're saying, like our cannonball example, if you want it to orbit the Earth, we have this tangential velocity, which means it's going in one direction, but because of gravity, we see this curvature, and so the tangential velocity will stay the same, but because it's accelerating, the velocity is changing. How does that make sense?
So its speed is staying the same, right? So when we talk
Okay.
about speed, you think of things like miles per hour, right? That's a speed. It doesn't have any direction associated with it. So if we're
Okay.
going 50 miles an hour, that's a speed.
Okay.
Now let's say that we're going 50 miles per hour to the west. This is now a velocity. And the
Because we
reason
have
why we have a
speed
direction,
and direction.
right? So we have
Okay.
that direction associated with it. So the reason why that matters is, let's say that we kept going 50 miles an hour, right? Your speedometer kept saying 50 miles an hour, but now instead of going to the west, you're going south. So you made a 90-degree turn and now you're going south, but you've stayed going 50 miles an hour the whole time. There's actually an acceleration that is happening during that time because you're changing direction. And so the
And
same, yes,
pretty sure everyone's felt that acceleration, right? If you are turning and you're still going relatively the same speed, you feel like it feels like a force is pushing you against like the side of the car one way or another. But it's not actually the force, right? It's just this change in velocity due to the acceleration.
exactly. Um, so if we come back to our equation here, we need to be able to associate our acceleration, but now we're changing our velocity. So we need to have our acceleration somehow be related to our velocity. And I am trying to remember this equation. I don't have it memorized off the top of my head right now.
Neither do I.
We're going to get there though.
Trying to get out the heavy duty book. See if that can help us out.
What heavy duty book? I'm pretty sure it's A equals V divided by R squared, but I could be wrong here. Okay. I know I'm missing something. Okay. Acceleration due to the change in the direction is, I had it backwards. It's V squared over R equals A. Okay.
Okay.
So we can go again and plug this in, and we get V squared over R is equal to constant for gravity m1 divided by R squared. And then again, using some mathematical math here, we can cancel out one of these
Ooh,
r's on
okay,
that
I
side
got it.
and that side, and we get v squared is equal to g
Yeah.
m1 over r.
Okay. And we could take that one step further, right? Get
Absolutely.
the
What do we do from there?
velocity without the squared. Nice.
So to do that, Jaden, what do we want to do?
We want to take the square root on both sides of that equal sign. Doing that will leave us with, there's a square root, there's a square root. Boop. Doing that will leave us with v equals big G m1 over r. All of that under the square root.
Cool, cool. Let's double check that that is the correct answer before we publish this and say that it is.
It is.
It is.
Big book confirmation.
So this question is solved. Okay.
Whew.
Dude, we did it right. Look at that. And we only had to look up one equation the whole time.
That was pretty impressive.
That's pretty good. So let's stop and think about this equation again for a second, right? So let's say that I am a NASA engineer and my goal is to launch a satellite into space. And I have now solved for this equation. What can I find out from this equation about trying to figure out the orbit of my satellite?
Well, we can determine how far away from the center of mass we need to be, and at what point that affects our velocity. Because we know this big G and little m for the Earth will be constant, right?
Mm-hmm.
So the only two numbers that we will change is the radius and the velocity. So those are our only two options, right?
Cool. Right. Hey, we have a quick question. I'm going to have you answer this one. It's from Kelsey. She's asking, where did the negative go? Jaden, you were Mr. Negative Man. You dropped a negative.
So in this situation, when we went from the acceleration equals the negative g over m1 over r squared, we were able to drop the negative because we care about the magnitude at this point. And a magnitude is the same thing as like an absolute value in math. So we don't actually need the negative anymore. Does that make sense?
I'm not sure if, sure, let's go with that, even though velocity is a vector, but, well.
Is that, what do you think, Kip? Let me look real quick.
I mean, we could switch the negative to the other side, and we would be in trouble still, because this is why I don't mess with negatives until I'm all the way done. Because this is, I think, Jaden, the reason why and where we messed up is if we go back a few slides here, just one slide. Oh, wait, what happened there? If we go back to this slide here, this is going to have a negative acceleration. That's where we messed up. So this should actually be a negative here. So the negatives on both sides cancel out. It's totally mathematical. Okay. Thanks for the question, Kelsey. That was a good question. Signs always
Yeah, thank
are
you.
trouble for me.
Boop, boop.
And there we go. Okay.
Cross those out now.
So like we were saying with the radius and velocity, right? So when you are sending a satellite to orbit the Earth, the only thing that matters is its velocity and its radius. So if I'm a NASA engineer designing, trying to figure out my orbit, the things I have to take into consideration is where do I want to put it? How far above the Earth do I want to put it? And if I'm trying to figure out how far above the Earth I want to put it, then what velocity does it need to have for that to work out? So if we wanted to, Jaden, do you want to keep going on this?
Yeah. We could
Kelsey
make
said
up
she liked your answer, and that's rude. For the negative thing.
No,
But
yours is
mine's
real
more
good.
correct. But so we can keep
I
going.
think also, depending on your reference frame, you can change negatives a lot.
Yeah, that's why I just don't mess with them until I have to. Okay.
Reference frames are a whole different discussion.
Yes, they are. Okay, so Jaden, do you want to try to solve for what velocity or what? Yeah. Or sorry, let's say, do we want to solve for how far away a satellite needs to be from the Earth for a geosynchronous orbit? For those of you that don't know, this is what GPS satellites use. The reason for this is they are actually traveling at the same speed as the Earth's rotation. So as the Earth is rotating, the satellite is rotating with it at the same speed, so it always looks like it's in the same spot.
Right. It's always falling at the same spot.
Exactly. So if we've got so what we need to do here is we've got the velocity, right, is equal to square root.
Geosynchronous, right?
What?
You said geosynchronous orbit?
Yeah.
Okay.
So my square root needs to go over the whole thing there. Okay. So in order to do this, we got to look up a few different numbers. We need to look up
Gravitational constant, the mass of the Earth.
Do you want to look those up? And
change.
while you're looking those up, I'll rearrange this equation to solve for the radius, because that's what we're trying to figure out, right? So the question is, what radius from the Earth does a satellite need to be at
Okay.
to have same velocity as Earth?
6, 7, 4.
Isn't it like times 10 to the negative some giant
11.
Number? Yeah, 11.
Yeah.
So we've got velocity. We're going to go ahead and square both sides, so we get velocity squared is equal to gm1 over r. And then from there, I'm gonna do a little bit of math here. So we're gonna time both sides by r, and we get r v squared is equal to gm1. And then from there we can divide both sides by v squared, and we get this is equal to r is equal to g m1 over v squared.
Okay, so we have m1 equals 5.9722 times 10 to the 24th. 5.9722 times 10 24, and that's in kilograms. Okay.
And then I'm looking up the rotation of the Earth right now.
Okay. Just how fast it.
Yeah, how fast it goes.
So are we solving for the radius then? Yeah.
Yes.
Yeah, we are. Okay. You just did some algebra and
Yep.
showed us. Cool.
You can double check it and make sure that it's right.
It looks beautiful, Kip.
Dude, I can't find it. I mean, I guess we could calculate it if we wanted to. Oh, here we go. So it rotates at 1,669.8, and that's kilometers per hour. So we got to do some quick math here. And
Get
switch
it in
that.
meters per second.
Alright, so this is going to be times 1,000 meters over 1 km, and then times 60 minutes over, or whoops, that's backwards. 1 hour over 60 minutes, and so we get
There you go.
6.
Are we
9,
doing meters per second or meters per minute?
Meters per second. Okay, 8.
Okay, so then
0, 0. And then we got, you want to take it from here? Or then this is divided by 6. This is going to be divided by 3,600.
Yeah. There we go. So 166. Is that 1669800?
Yeah.
Divided by 3600.
See, this is why I like to just be a physicist, because we never actually have to use numbers, and we would have been done with this question a long time ago.
Okay, so that is approximately 463.8 meters per second.
Hold on, Jaden, we might be having a... Not sure what's happening here. Huh, okay. Yeah, so we've got... Sorry, what was it? We've got some questions here from Kelsey.
463.8 meters per second.
463 meters per second. Okay. So really quickly, from Kelsey, she asked, how do they find the mass of the Earth and the velocity and gravity?
Okay. Gravity is you could find gravity yourself by doing several tests, and you'd get a really good approximation of it. Some tests you could just drop different items from a building and have a timing system to measure that, and you can measure the force of gravity that way. how do we find the mass of the Earth, Kip?
So really quickly, Jaden, with what you were saying about finding gravity, I'm not sure. I like your answer.
Was she talking about the gravitational constant?
I'm not sure. I think that in part she may be. The gravitational constant they actually calculated in quite a crazy way. This guy actually had two metal balls that he had that were really big and heavy, and he set them up on kind of this weird, pendulum type thing, I guess, so they could rotate back and forth. And he knew the mass of the ball, and then he knew the mass of um, another ball that he was holding, right? And he held them super close to each other enough that he could measure, the radius behind them. And there was so little other forces acting on it. He was actually able to get these masses to barely move. And from that's one way they were able to calculate the gravitational constant.
It's crazy how people just think of these things,
Yeah. It's all about solving for everything so you only have one unknown. I'm trying
Yep.
to remember the history behind finding the mass of the Earth, but this is something they've actually known for a very, very long time. Like over 500 plus years, I'm pretty sure. And I'm trying to remember exactly how they did it, but they calculated it, I'm pretty sure, based off of orbits. And they were able to get pretty close to the actual mass that we now know. And then the velocity, again, they first knew what the radius was of the Earth was, and to find velocity of an object, it's just simply going to be, what's here? It's revolutions to linear speed. Are we dividing by R? Or are we multiplying by R? We're multiplying by R. It's just simply revolution. So in the case of the Earth, it does one rev every 24 hours. And so if we times that by the radius, R times 24, that would give us the velocity of the Earth. Now, how they found out the radius, I'm not sure. Or they could have found out the velocity first and then found the radius that way. That's probably what they did, but I can't.
Yeah.
That's probably more accurate to the way they did things. Okay, so let's keep moving on here. So we've got 463 meters per second. And so we've got this equation up here. So we just plug it in and we get 6.67. You gave me a lot of numbers there, times 10 to the negative 11.
You don't know how accurate you want to be,
The important thing is, are we at the same sig figs on all of our numbers, Jaden? Because it's not looking like that. Okay. 463. All right. So now we plug that into a calculator and we get what?
One moment, I am typing it in. And then let me put some brackets, because parentheses are important. And that is.
See, I'm telling you, this is why I like just, doing physics without numbers, because we would have been done like 20 minutes ago. We could have moved on.
It is much easier, isn't it?
Much, much easier.
Okay, so let me just quickly verify. You forgot your squared on the 463.
Yes, I did. Thank you very much.
So let's just double check. Okay, our result is one. How many sig figs do you want?
Dude, I don't care. You choose.
1.84 times 10 to the ninth.
This is meters. So this is meters from the center of the Earth. I
Yeah.
don't know if we want to go and figure out from the Earth's surface. I think we're good enough. If you
Yeah,
want to figure
I think
out
so.
this question is solved. But if we wanted to figure this out from, all we'd have to do is subtract the radius of the Earth here, and that
The
would,
distance from the center to the
yeah,
surface.
exactly. Cool, dude. Anyone got any
Sweet.
questions out there? Anyone at all want to ask us anything before we sign off? Preferably math or science related. If anyone,
They just ask us something about English.
yeah, please
We're
don't
the
ask.
wrong people to ask that question.
Yeah. Well, you might know the answer. I definitely don't know the answer. As you can see from up here where I was writing, and I was like, I'm just gonna scribble because I don't know how to spell anything. Oh,
Yeah.
Angie said she emailed one, I guess, and I didn't get notified, so let's.
Oh, she said save it for next time. We can take a look at it, see if it's easy.
It's more
Question or
of
not.
it's more of a thought-provoking question more than anything. It says, what level of math do you think high school students should be required to take? Do you think math is taught in the appropriate order? Whew. I think the way they teach math in high school is horrible.
Do you want to save this for next time?
Sure, we can go on a whole large rant about why
Yeah, we could.
why math is stupid in high school and why I don't blame people for hating it. But yeah, real quick, Jaden, are we gonna be doing a Thanksgiving live special, or are we just gonna skip on by Thanksgiving? I'm good either way. So
I'm
you in
good
the
either way.
comments, donate some money if you want a Thanksgiving special.
Yeah. Get us to 5 likes.
Yeah, I think we're currently sitting at 10 subscribers. If you guys can get us up to 20 subscribers by Thursday, we'll do a Thanksgiving special.
That sounds good to me.
We'll do turkey math. But,
Hey.
cool.
And if you're interested to know more about orbits, Kip and myself are happy to do more research and let you all know
Yeah,
anything else you want to know about it.
we appreciate all your questions, even those questions that we don't have the answers to, because we will research them and then we get to learn more things. So for
Yeah.
Kelsey's question about the how they figured out the mass of the Earth, that will be a great question to research, and we can talk about it next time.
Yeah. I definitely remember learning about it, but
I do too, but I don't remember. It had something to do with orbits. That much I do know.
yeah. And this equation that we've dealt with.
Yeah.
Well, did they find the gravitational constant first?
I don't think they did.
Okay. Well, if they did, then we could just say the mass of something we know, solve for the Earth's mass. That way.
I think I actually think it had to do with Kepler's laws. Kepler came up with some big laws back a while back.
Okay.
And they were related to energy. Um, and
Oh yeah, we have gravitational potential
right,
energy and
exactly. And I think
uh
that that's how they came
yeah.
through to figure it out was something to do with the potential energy. And knowing how fast the Earth was traveling through space by, I think he'd measured by stars or something like that in the sky, and was able to come up with it.
So the first time that the Earth's mass was measured with any accuracy, it was within 20% of the correct value, and that was in 1770s.
Okay, so 17. I
And
was a little
then
later than what I
within
thought.
and then within a 1% value, it was Cavendish experiment,
Right.
and that was 1798. So if you're interested, look up Cavendish experiment and you might be able to find more about what he did in 1798.
Okay. And maybe we can go through it a little bit next time. But this
Yeah.
right here, for all you flat earthers out there, um, proves that the Earth is not flat, or else our satellites would be in big trouble. They would
Yeah, they
just,
would be.
if the Earth was flat, they would eventually just hit the ground, or they would fall off whatever thing we are on and just keep falling. So,
Okay.
alrighty. Well, let's call it a night. I'm gonna sign off. Please
Yeah.
like and subscribe down below. You know the drill. 20 subscribers, we get a Thanksgiving special. If not, we'll see you next Tuesday. Bye now.
Sounds good. Okay. Adios.